Have you ever wondered how a computer tells a machine to carve a block of solid metal into a specific shape? To understand how it works, take a look at these airplane propellers. Notice those smooth, complex, swooping curves. Now picture a standard, blocky metal gear. Between the two, which one do you think is easier for a robot to make? Creating those smooth, flowing shapes requires a process where the cutting tool moves left, forward, and down, all at the exact same time, like writing down a twisting slide. This takes a massive amount of computational power, time, and money to calculate and execute. But if you open up the hood of your car, or look inside your computer and household appliances, you'll notice something right away. The vast majority of the parts inside don't actually have those expensive, sweeping contours. Look at these heavy mechanical gears. Instead of sculpted waves, they are built almost entirely out of flat faces, straight slots, and deep, distinct holes. Because these shapes are so common, engineers developed a specific manufacturing method exclusively to carve them. It's called prismatic machining. By sticking strictly to these distinct, flat levels and avoiding those complicated 3D curves entirely, manufacturers save immense amounts of time and money. It's a clever shortcut for building the everyday parts around us. The secret behind this shortcut is a technique called 2.5-axis machining. I know, having half an eye though, but it actually makes perfect sense once you see it in action. In this diagram, you can see how the first two axes work. Think of it like drawing on a flat digital tablet. The cutting tool moves freely side to side and forward and back to carve out a flat two-dimensional shape. It stays at exactly one depth the entire time. Here is where the 0.5 comes in. The tool completely stops its flat side-to-side drawing. Instead, it drops straight down like an elevator to a new, specific depth and locks itself firmly into place. Once it's locked in at that lower level, it goes right back to drawing a flat, two-dimensional shape. By repeating this process, the machine builds the part layer by layer, almost like a staircase, rather than a smooth, continuous ramp. Remember that twisting slide from earlier where the tool was moving in 3 directions at once? By separating the downward drop from the flat carving, the math becomes incredibly simple for the machine's computer to calculate. So 2.5-axis machining is really just flat, two-dimensional cutting performed at multiple distinct depth levels. It allows us to carve complex-looking, stepped parts with incredible speed and efficiency. This image shows early computer mainframes from the first years humans began using digital data to control factory machines. It reminds us that long before a robot physically cuts into a block of metal, the human's idea has to be translated into digital data. This process starts in a digital environment called CAD, or computer-aided design. This is simply the 3D software where human engineers draw their parts and build a digital blueprint of exactly what they want to create. Next comes the software that acts as the crucial translator, CAM, or computer-aided manufacturing. CAM takes that human-drawn blueprint and figures out the actual physical steps a robot must take to build it. Look at this 3D model. When we bring it into the CAM software, it begins a sort of digital shape hunt. The computer automatically scans the digital block and identifies the specific geometric shapes, highlighting a pocket, then a hole, and finally a straight slot. For each identified shape, the software automatically maps out the exact route the cutting tool needs to take to hollow it out. It then translates those routes into lines of code that the physical machine can read and follow. Linking the design software directly to the manufacturing software removes the need for a human to manually type out thousands of lines of machine instructions. It creates a clean, error-free pipeline straight from human imagination to automated physical reality. In this photo, you can see a human operator interacting with an early milling machine. Before these software systems were connected, workers had to manually calculate and program every single movement the tool made, which took hours, if not days, for a single part. Today, the software can even invent highly optimized routes, like the strategy for clearing out bulk material using circular loops. Instead of just driving the tool straight forward through a heavy block of metal, it takes a continuous, overlapping path. That specific circular looping keeps exactly the same amount of metal pressing against the tool at all times. This constant workload prevents the machine from breaking down under stress and lets it carve out material incredibly fast. The results of this automated, layered cutting process are all around you. Look at these common metal hinges. You can clearly see the flat, stepped layers and the distinct drilled holes. So the next time you pick up a metal phone case, install a bracket, or open a door hinge, take a closer look. If you see those flat levels and distinct geometric holes, you're looking at the telltale signs of prismatic machining, quietly carving our modern world one perfect step at a time.